Hello friends, so today we are going to solve the question from heat and thermodynamics, and in this we are going to solve questions from the year 1997, and we are going to solve total 5 questions. So the first question, it states that the apparatus shown in the figure consists of 4 glass columns connected by horizontal sections. The height of 2 central columns B and C are 49 cm each. The 2 outer columns A and D are open to the atmosphere. A and C are maintained at a temperature of 95 degrees centigrade, while the columns B and D are maintained at 5 degrees centigrade. The height of the liquid in A and D measured from the baseline is 52.8 and 51 centimeter respectively. Determine the linear coefficient of thermal expansion of the liquid. So in this case, the basic figure is given to us. We are having tubes which are connected horizontally, and various levels are, or we can say tube are, you can say labeled as A, B, C and D, and the respective temperatures of the tube is given that A is 95, B is 5, C is 95 and D is at 5 degree centigrade. And the height of A and D is also given, and they are at different levels. A is on the little bit on the higher side as compared to our D. So in this case, first of all, we have to use a standard formula that gives us the relationship between the density of a liquid at a particular temperature and with respect to that temperature. Okay. So we can say density of liquid varies with temperature, and that relationship is our rho T is equal to rho naught 1 plus gamma multiplied by T. Okay. Here this is gamma, and in this case gamma is our coefficient of volume expansion. So you can say our gamma is our coefficient of volume expansion, and rho naught is the density at 0 degree centigrade at 0 degree centigrade, and this rho T is the density at a certain temperature T, which we can just find out. So we are having two temperatures, one is 95 and other one is 5 degree centigrade. So we can modify this particular formula based on the temperature. So we can say density at 95 degree centigrade and for that we can write this as rho 95 is equal to rho naught 1 plus 95 times gamma. And similarly we can write density at 5 degree centigrade, density at 5 degree centigrade. So we can say rho 5 will be equal to our rho naught 1 plus 5 times gamma. Okay. And in this case, as we can just assume that every liquid column is imbalanced, okay, because of the temperature variation, the height of this liquid column is, we can say, at the bottom level the pressure is same throughout, okay, because it is basically connected apparatus. So we can say that the effective pressure balance according to their respective columns, it can be calculated by equating the pressure at the equivalent points. Equivalent point means at the level connected in B and C, and similarly we can find out for the other part also. Okay. So we can say pressure balance and as the apparatus is connected, apparatus is connected, therefore we can say that the pressure at the bottom which we can also call as a baseline, is same throughout, Okay. And therefore we can also draw a conclusion that the effective pressure balance accounting for the columns is calculated by equating pressure at the equivalent points. And according to figure, two equivalent points are obvious to us, that are point B and point C, because they are equivalent points. Okay, so we can say this as a B and C. Okay, so we are going to start from the open end and move to the other point also. So we say from open ends, and we know that our A and D are open to the atmospheric pressure. So you can say this point A and D are at atmospheric pressure, and it is a P naught because it is open to the atmospheric pressure. So first path is from A to B. Okay, so we can say that path through A to B, we can write that the pressure drops through A, and for A, let us assume that the height of that column is h1, density because of 95 degrees centigrade is rho 95 multiplied by G, minus rise through B, and B we assume is having a height h, temperature is over 5 degrees centigrade, so this comes rho of 5 multiplied by G. Okay. So this was path through A to B. Now we come to from D to C. So you can say path through D to C, and from D to C we can say pressure drops through D, pressure drops through D, and D we can assume height of h2, and the temperature is over 5 degrees centigrade and above G, and minus rise through C, and both this B and C are at the same height, so we can write this as h. Temperature is different, so this comes as 95 and multiply by G. Okay. Now we can equate pressure at the bottom. So you can say equating pressure at bottom, and therefore we can write our P naught plus h1 rho 95 G minus h rho 5 times G is equal to, towards the our you can say right side, and this comes as our P naught plus h2 rho, and this is our 5G minus h rho 95 times G. Okay. So we can just, so we calculated the pressure at the bottom. Okay. And we assume that the height of this B and C will be same, that is h. Height of this liquid column at A is our h1, and toward D it is h2. Okay. And we are having the atmospheric pressure P naught, and here also we are going to have atmospheric pressure P naught. Okay. And here our P naught and G cancels out throughout, so we can write this will be equal to our h1 rho 95 minus h rho 5 is equal to h2 rho 5 minus h rho 95. And we can just combine our with respect to their densities. So we can say our rho 95 will be our common. This will be h1 plus h is equal to rho 5 on the other side. We come this as h2 plus h. And from here we can write the ratio rho of 5 upon rho of 95 will be equal to, we have this as h1 plus h divided by h2 plus h. Okay. And we can just substitute the values, and we can write this as rho of 5 upon rho of 95, H1 is our 52.8 plus H is our 49 and H2 is our 51 and H is our 49. This comes as our 101.8 and divided by 100. Okay. So this ratio will be equal to over 1.018, and we also know that this is our individual equations for row of 95 as well as row of 5. Okay. And we can just you can say take the ratio and substitute it here the left side. So we get this as our 1 plus 95 times rho divided by 1 plus 5 times rho is equal to 1.018. And now this is quite simple to solve. So we can say that our gamma will be equal to, this will be coming as our 2 into 10 raised to power minus 4 approximately. So we can say gamma will be approximately equal to 2 into 10 raised to power minus 4. And we have to find out the linear coefficient. Linear coefficient is represented as alpha, and this alpha is approximately equal to 3 times, sorry, gamma is approximately equal to 3 times of alpha. Okay. So we are supposed to linear coefficient expansion, linear expansion coefficient, which is denoted as alpha, and this is approximately equal to gamma divided by 3. And we simply substitute the value, we get alpha is equal to is 2 into 10 raised to power minus 4 divided by 3, and approximately this will be coming equal to as 6.7 into 10 raised to power minus 5. So this is our linear expansion coefficient that was asked us for us to calculate. Next question. It was asked in the year 1997, and it states that a sample of 2 kg monoatomic helium assumed idle is taken through a process ABC. Another sample of 2 kg of the same gas is taken through the process ADC, given the molecular mass of helium is 4. Okay. So based on this we have 3 questions, but basic you can say process for ABC and ADC is given to us. So the common start point of both the processes is our A, and the common end point for both is our C. The paths are different. One is from A, B and C, and other one is from A, D and C. Okay. So from the figure we can just say that for the first, for this AB it is basically at a constant volume, and from A to D it is basically at a constant pressure. Okay. Then they are going to change its positions. And so we are given that, and both samples are of 2 kg. Okay, so we can say that the mass of helium sample which is small m, it is given to us as 2 kg, and molar mass of helium is given to us as 4. So from here we can find out the number of moles. So we can say our number of moles will be equal to mass divided by its molar mass. So this is 2 divided by 4, and this will be 2000 grams, and it will be coming as 4 gram 500 moles. And we are given it is a monoatomic, therefore we can write that our its C of V is equal to 3 by 2 times R, and R is a standard value. And from the figure we can write, or we can say, we can call this a PV diagram. So we can say that from PV diagram, we have state A. So state A, it is having a volume of 10. So we can call this as state A is have a volume of VA, which is given as 10, and it is having a pressure of PA, and that is given as 5 into 10 to the power 4. Similarly, we can write for our B, that is our VB is also our 10, and pressure at B is our 10 into 10 to the power 4. And then we have our C, so we can say our VC 20, pressure at C is our 10 into 10 to the power 4, and finally we are having our D, that volume of D is our 20, and pressure at D is our 5 into 10 to the power 4. Therefore, we can also draw a conclusion from this PV diagram, and we can say that for process ABC, we are having this A to B is our isochoric heating, and from our A to B, and we have B to C, and we can call this as isobaric expansion. And then we have our second process. Second process is our ADC. Is our ADC, and for that we can say our A to D is our isobaric expansion, and we are having our D to C, and that D to C is isochoric heating. So this conclusion also we can draw from our this PV diagram, and from all these state we can find out the corresponding temperature also. And for finding out the temperature, we can use the standard gas equation, that T is equal to PV nRT. Therefore, we can write that our temperature at A will be equal to a PA VA upon N multiplied by R, and this will be approximately equal to 120.3 Kelvin. And we have our temperature at B, same formula, that is VB this is our PB VB upon N times R, which will be approximately giving us 240.6 Kelvin. And similarly we can say our T of C will be equal to 481.3 Kelvin, and we have our temperature at D, that will be equal to over 240.6 Kelvin. And so this was our part A, finding the temperature at all the relevant points. And part B states that, is there any way of telling afterwards which sample of helium went through the process ABC, which went through the process ADC, write yes or no. Okay. And in this case, it is not possible to tell that which process went through which, because the initial state is same, that is our A, and the final state is also same, that is our C. So some of the, you can say, there are some properties which are state function, that temperature, internal energy, and etc., which are only dependent upon the current state, not on the path taken. Okay. So it is not possible to tell that which sample is going to take place. Okay. And if we need a path particular dependent calculation, then we need certain more information, such that we have to take care of the amount of work done, or we can say whether amount of heat absorbed or heat released. So this more or less is going to give us a better picture that which path is being followed, okay, whether it is ABC or whether it is ADC. Okay. But basically we cannot tell that which path is being taken. So part B states no. And part C states that how much is the heat involved in the process A, B, C and ADC. Okay. And so we solve for part C. And so both processes, means our process ABC and ADC, both processes starts from A and end at C, and similarly for the other part also. Okay. So we can say that in both these processes the change in internal energy will be our same, okay, because it is path independent. Therefore we can write that our delta of U will be equal to N of C of V multiplied by our TC minus TA, and which gives us as 500, and this is 3 by 2 multiplied by R. The R is our 8.314, and temperature is our 481.36, and we have this as 120.34, and we get this delta U, change in internal energy, will be approximately equal to 2.25 into 10 raised to the power 6 joules. Now we can use the first law of thermodynamics. So we say that from first law, we have delta Q is equal to our delta U plus delta W. Okay. So we have two paths or two processes. We divide this first law according to our both the processes. So we start with process ABC. Process ABC. So from there we can find out the work done for our path ABC, and that will be our from A to B plus and B to C, or we can say work done from A to B and work done from B to C. And work done for our A to B is basically our 0 because it is isochoric process. So for this we can say this work done is equal to 0, and for our B to C is our isobaric. So we can use the formula that our delta W for B to C can be written as our pressure at B, and we have volume at C minus volume at B, and this portion we can calculate. So let me calculate it here. So I get my WBC will be equal to pressure at B is our my 10 into 10 to the power 4, and volume at C is our 20 minus 10. So we get that the work done in BC will be equal to 10 to the power 6 joules. So from here we can say that the work done for the process ABC will be equal to 0 plus 10 to the power 6, which comes as 10 to the power 6 joules. And from here now we can easily find out the heat. So we can say our delta Q ABC, and delta U we found out, delta W we found out. So this comes as our 2.25 into 10 to the power 6 plus 10 to the power 6, and this will be coming as our 3.25 into 10 to the power 6 joules. So this is for our ABC. Same we are going to do it for our ADC also. So we can say our process ADC. First of all, because energy will be same in both, and change internal energy delta U same, so we have W ADC, and this comes as our W from A to D plus W from our D to C. Okay, and this A to D is our isobaric, same. So we can say this as WAD will be equal to our pressure at A, volume at D minus volume at C. And for our work done D to C, which is our isochoric, so this work done will be equal to 0. And we can find out our this delta WD. So we can say delta WAD A to D will be equal to pressure at A is our 5 into 10 to the power 4, and this comes our 20 minus 10, giving us 0.5 into 10 to the power 6. So we can say that our total work done, that the WADC will be equal to 0.5 into 10 to the power 6 joules, and therefore the heat for our ADC will be equal to delta U delta U is same, that is 2.25 into 10 to the power 6 plus 0.5 into 10 to the power 6. So this gives us that our delta Q for path ADC will be equal to 2.75 into 10 to the power 6 joules. Okay, so this was our part C. Next question. It states that 1 mole of diabatic ideal gas gamma 1.4 is taken through a cyclic process starting from A. The process A to B is adiabatic compression, B to C is isobaric expansion, C to D an adiabatic expansion, and D to A is isochoric. The volume ratio of VA to VB is 16 and VC to VB is 2, and the temperature at A is TA, that is 300 Kelvin. Calculate the temperature of the gas at points B and D and find the efficiency of the cycle. So we have to find out the temperature at B and D, and we know that from A to B, because temperature of A is given to us, so we can take that as a reference, and from process of A to B is our adiabatic compression. Okay, so we are going to make use of that. So you can say temperature at point B and D. Temperature at B and D. And for temperature at B, let us call this as our TB, and temperature at D, let us call this as our TD. And the process that our A to B, this is given to us a adiabatic compression. Adiabatic compression. Therefore, we can write that our temperature volume gamma minus 1 should be equal to constant. And we can just modify into according to the points, and we can write this as our TA VA gamma minus 1 is equal to TV VB gamma minus 1. So this gives us the temperature at B will be equal to temperature at A, and we have this as volume at A, volume at B, and gamma minus 1. And the ratio is given to us as 16, and value of gamma is 1.4. And so we get this as 300 multiplied by 16, and we have 1.4 minus 1. So we get that our TB, temperature at B, will be approximately equal to 909.43 Kelvin. Okay. And next is our from B to C, that is our isobaric expansion. So we have our B to C, this is our isobaric expansion. And so for ideal gas at constant pressure, we can write that our temperature is directly proportional to volume. Okay. And this is at constant pressure. So when P is our constant, and therefore we can write that our Tc is equal to Tb multiplied by our Vc upon Vb. Tb we just found out is our 909.43, and the ratio of Vc upon Vb is given to us 2. So temperature at C comes as 1818.86 Kelvin. Now we can come to a final, that is our point D. So we are having C to D, and our C to D is our once again adiabatic expansion. Adiabatic expansion. So we can directly write it now as temperature at D is equal to temperature at C, and this comes as Vc upon Vd gamma minus 1, and we substitute the respective values. We get this as Td. Tc is our 1818.86, and the ratio is our Vc upon Vd, and so we can, one second, okay, so we can write the ratio of Vc upon Vd, and that will be equal to our 2 upon 16 gamma minus 1, that is our 1.4 minus 1. So this gives us our Td is equal to, this will be coming close to as 791.7 Kelvin. And we are left with now efficiency part. So we can say the efficiency of the cycle so we can write that our efficiency will be equal to our 1 minus our heat released, or we can say this is heat as output, divided by Q epsilon. Okay. And here this Q epsilon is our heat absorbed and this our Q out is our heat rejected. So we are going to find out both heats. So let us start with the heat absorbed. So we can say that heat absorbed during isobaric expansion which is basically from our B to C, we can write this as Q epsilon is equal to our C of P, and his Tc minus TB. Okay. And this C of P is our standard formula, which gives us our, you can say, gamma multiplied by C of P. So we get this as 1.4 multiplied by 5 by 2 times R, and this will be coming as our 7 by 2 times R. Okay. And we can also find out our heat rejected. Heat rejected during isochoric process. Isochoric process, which is from D to A, and we are only interested in magnitude, so we can just put it inside the magnitude part, and that will be giving us C of V is equal to TA minus TD. Okay. Or we can write it other ways also, it doesn't matter much. So we can write this as our TD TA because TD is greater than TA. So we just reverse it. Now we substitute the value, and we get our efficiency 1 minus, this comes as our C of V, that is TD minus TA. C of P is our TC minus TB, and this will be equal to 1 minus, and we substitute the value, we get this over 719.7 minus 300 divided by 1 second. TC is our 1188 0.6 minus, and TB is our 909.43, and this whole term is our CV of, and multiply by 1 upon gamma, and in place of gamma we can just put 1.4. So we get our efficiency will be approximately equal to 61.38%. Okay. And we can also represent this entire process as a PV diagram also. It was not asked, but still we can just plot it. So this is your pressure and this is your volume, and we start from A. So this is our point A, and it says from A to B is our adiabatic compression. Okay. And so adiabatic compression we can represent something like this. So this is our point B, and their respective ratios are given to us. So here we are having a V0, and this will be our 60 times V0. okay, and it is moving in this direction. And from B to C, we are having a constant pressure. So this is our point C, and the pressure is our, suppose, P naught. And then once again it's adiabatic process. Okay. It must be more symmetrical. So it will use something like this, and it will be a symmetrical path this way. So this will be a point C, and this is point D, and this will come back to A. And so the pressure at C will be nothing but our 2 times V naught. Okay, so this is the PV diagram of our this the question. Next, it states that a double pane window used for insulating a room thermally from outside consists of 2 glass sheets, each of area 1 meter square and thickness 0.01 meter, separated by a 0.01 meter thick stagnant airspace. In the steady state, the room glass interface and the glass outer door interface are at constant temperature 27 degrees centigrade and 0 degrees centigrade respectively. Calculate the rate of heat flow through the window pane. Also find the temperature of the other interfaces, given the thermal conductivities of glass and air are 0.8 and 0.08 respectively. So in this case, we can assume that the entire system is consisting of or basically it is a composite system. So we are having a composite system and that composition system consists of our glass and then it is our air, and then once again it is our glass. Okay. And this is a symmetric you can say composite system. The width of the glass on the both side is our same, that is our 0.01 meter thick, and this is also 0.01 meter thick, and air is of different thickness, that is our 0.05 meters. So this is our composite, and this area of this entire of all these is same, and this is given as area is equal to 1 meter square. And it is also given that the temperature across the window is from 27 to 0 degree centigrade. Okay. So we can say that our temperature difference across the window is from 27 degree centigrade to 0 degree centigrade. Okay. From yes, and so these are the things, important things which are given to us, and we have to remember that the temperature, everything is at steady state. So we are going to find out the thermal resistance of each layer. Each layer means for this glass and glass it will be same, and for our air we are going to find out separately. So we are going to find out total resistance, and from there we can easily calculate the rate of heat flow. Okay, then we move toward the temperature part. So you can say the thermal resistance is And thermal resistance, we start with our glass, so we can say for each glass layer and let us call this as our R of G, where G stands for glass, and that will equal to 0.01, which is their thickness, and area is our 1, and we are given is thermal conductivity is 0.8. So this comes as 0.8 multiplied by 1. So this comes as our 0.0125. Okay. And similarly, we can write for our air. That is our R of A will be equal to, its thickness is 0.05, conductivity is our 0.08, and area is same. This will be coming as 0.625. So you can say the total resistance total thermal resistance let us call this as R of T will be equal to, okay, and it will be a series combination because the heat flow will be from sequential, one after the other. So we can say this will be equal to our 0.0125 plus 0.625. So we get this will be equal to 0.65. Now we can find out our rate of heat flow. Rate of heat flow will be equal to Q, that is our temperature difference 27 minus 0, and the total resistance, that is our 0.65, which will be giving us 41.54. Okay. And we can also write their general formula. Okay, so this thermal resistance, we can write this thermal resistance will be equal to our D upon K A. D is our thickness, K is our the coefficient, and A is the area. And our this heat flow is our change in temperature divided by thermal resistance in this case. Okay, so these are the two formulas which we have used. Now we can find out that the temperature at other interfaces. So we have two interfaces. Okay, so we can just draw an approximate figure for that. So this is suppose our glass 1, and this is our glass 2, and in between it is air. So there will be two interfaces, one will be glass 1 and air, and other interface will be the air and glass 2. So we are going to have two interfaces. So we can say temperature at interfaces, we are having glass 1 and air interface, and this can be written as our And for this we are going to use the formula, and that formula is our Q multiplied by thermal resistance. Okay, so we get this glass 1 multiplied by air, and we are having our okay, let me explain in this way. So we can say that the temperature drop across each layer is Q multiplied by R for that layer. Okay, let me put it. We can say that temperature drop across each layer is Q multiplied by R for that layer. For that layer, starting from our room side, surface, which is at 27 degrees centigrade, and ending at outdoor side, surface, which is at 0 degree centigrade. Therefore, we can say towards the left we are having a room whose temperature is 27 degrees centigrade, and toward the right we are having outdoor and whose temperature is 0 degree centigrade. Now we can just find out there. We have our glass 1 and air interface, and that will be equal to our 27 minus this is our Q multiplied by 0.0125, and Q we found out is our so we can say this will be equal to our 27 minus Q is our 41.54 multiplied by 0.125. So this comes approximately equal to our 26.48 degree centigrade. Now we come to the glass 2 and air interface, air and glass 2. Air and glass 2 interface, and that will be equal to over Q times 0.0125, because the temperature at their outside will be 0, so we can just put minus of 0, which will be not much of the use. So we substitute this, we get this as 41.54 multiplied by 0.0125. This will be coming as 0.52 degree centigrade. Is this the correct one? Q and I think so. Okay. Next question. It states that Earth receives 1400 watt per meter square of solar power if all the solar energy falling on a length of area 0.2 meter square is focused on a block of ice of mass 280 gram. The time taken to melt the ice will be dash minutes. Latent heat of fusion for ice is given to us. Okay. So here this is my, you can say, assumption that it should be ideally mentioned in the question itself, but it is not given. We can just presume that the ice is already at a melting point, that is 0 degree centigrade. Okay, so it means basically only the latent heat of fusion is required. Okay, there will be no need to change the temperature. So this is the important part here. So we can say that our ice is already at its melting point. That is 0 degree centigrade. Therefore, only latent heat of fusion is required. So if we do not assume this, make this assumption, we have to make, you can say, the temperature to come of this ice up till 0 degree centigrade. So some of the heat will be lost in raising the temperature of our ice up till 0 degree centigrade. Okay. And also there will be no losses, which is more or less is clear. So first of all, let us find out what will be the power received by the lens. Power received by the lens, and that is our P will be equal to solar the intensity of the light, or we can call this as solar intensity multiplied by area of the lens. Therefore, we substitute the values, we get our P is equal to 1400 multiplied by 0.2, giving us 280 watts. And energy required to melt the ice. Energy required to melt the ice, which is our Q is equal to mass and latent heat of fusion. So we substitute the value, we get our Q. Mass is our 0.28 multiplied by latent diffusion is given to us as 3.3 into 10 to the power 5. So we had Q is equal to, this will be our 92400 joules. So now we can just find out the time to melt the ice. Time to melt ice, that is our T, is equal to Q upon P, and we have to do in minutes, so this is our 60 will be equal to 92400, and this is our 280 multiplied by 60. Therefore we get our time T will be equal to 5.5 minutes. So this is equal to 5.5 minutes. So this completes all the 5 questions from the year 1997. Thank you.